हेलो क्लास। आज हम कंटिन्यू कर रहे हैं अपने प्रीवियस लेक्चर को। सो इन लास्ट लेक्चर वी विल डिस्कस पेंडल मिक्सिंग लेंथ concept. So here this is the pendle mixing formula. This is for laminar and this is for turbulent case. Now today continue our lecture. Today's topic is velocity distribution in turbulent flow in pipe. Now here is the tau is equals to rho L square du by dy square. Now here L equals to ky. K is the Karman's constant and its value is 0.4. So put the value of L, which is equals to ky. So here du by dy is equals to 1 by ky root of tau by rho. So this is tau by rho is known as shear velocity. This term is called as shear velocity, so it will represent by u star. So du equals to u star by k by dy. Now integrate this portion. So after integration, it is u equals to u star 1 by y is ln, that means natural log y plus c. Now apply boundary condition because we want the integration constant. So at the boundary condition y is equals to r, when u is equals to, when y equals to r, then u equals to u max. So u max is equals to, put the value. Now we want get c value, so put the values of y equals to r and u equals to u max. So here c equals to u max minus u star by k natural log r. Now this value put in this equation. So here is the velocity formula. So u equals to u star by k ln y plus u max minus u star by k ln r. So here is ln function and this is the ln function, and between this function there is negative sign, so it will convert it y by r. U equals to u star by k ln y by r plus u max. And the relation between natural log and log 10 base is 2.303 log 10 base. We can write natural log is equals to 2.303 log 10 and k value is 0.4, so divide by 0.4 it will give 5.75 u star log 10 base y by r plus u maximum. This is the velocity equation at the depth y for pipe. Now the above equation, this equation called as Pendel's University velocity distribution equation. Now for turbulent flow in pipe, so here this equation is used for both smooth and rough boundaries. So here u minus u max by u star. So u max is here, u minus u max and u star divided by u star is equals to 5.75 log y by r, and u minus u max is called as velocity differential. Now hydrodynamically rough and smooth pipes, so there is k value which is termed as average size of boundaries. So this is the boundary roughness. So here, if the laminar sublayer is large and the eddies does not penetrate to the boundary, so it will penetrate till the boundary, then boundary acts as hydrodynamically smooth surface, smooth boundary. And whereas in thickness of laminar sublayer is small and eddies penetrate up to the boundary, so this boundary said rough boundary, hydrodynamically rough boundary. Then is the penetration is large, that means the surface is more rough, so it will rough boundary. So here is the thickness of laminar sublayer directly proportional to density, dynamic viscosity, velocity, and the Reynolds number. So here is the directly proportional to the dynamic viscosity, inversely proportional to the velocity, and inversely proportional to the Reynolds number. Now, as per the Nicoretze experiment, Nicoretze has an experiment and it will give, that means K is the average size of the boundary. This is K, average size of the boundaries, and the thickness of the sublayer is less than 0.25 for hydrodynamically smooth boundary, and K by delta dash. Delta dash represents laminar sublayer thickness of laminar sublayer. So K divided by delta dash is greater than 6 is in categorized for hydrodynamically rough boundary, and R is the Reynolds number, which is equal to U star K by nu. Nu is the kinematic viscosity, and U star, we know the U star is root of tau by rho. So here Reynolds number is greater than, less than 3 is smooth boundary, and Reynolds is greater than equal to 70 is termed as rough boundary. Okay, the class is over.